Okay, so hi guys. How are you guys doing today?
Good.
Perfect. So please remember once again, we have an exam from 2 weeks from today. Okay, so what I'm gonna do is I'm going to cover chapter 4, hopefully also on Wednesday, and then we'll try to cover chapter 5 Friday and next Monday, and I'll try to keep next Wednesday and Friday as a review session. So that means there'll be not much of the chapter 6 will be included in exam 1, only a few, and then in exam 2, the later part of chapter 6 will be included in exam 2 at the mid-November. Okay. So those of you who completed late, please come here, grab this one. Come here, huge group. Yeah, come over here. Please grab this. Yeah, here you go.
Thank you.
Thank you. Thank you. Thank you. Okay. All right. Okay, so make sure we have an exam in 2 weeks. That's the one of the important schedule and our semester. So here we go. Did you guys watch the last Friday lecture? We good? Okay, perfect. So what we did on Friday was we tried to do the nomenclature for cyclic alkane. So if you have a 6-carbon member ring here, ring structure. It's just pretty much the same that we did for the regular alkane in chapter 3. You know, we just put hex, right? And then they're all in the single bonds between carbons in this group, so the A and E. But in the ring structure, additionally, you only need to do cyclohexane. This is how you can name this one. And then later on, whenever you have substitution groups like methyl groups or maybe ethyl groups over here, you can try to name those on your prefix, right? So it'll be one methyl, one ethyl, but make sure you guys always try to follow the alphabetical order. So this is methyl group, methyl group, ethyl group here. And here's the thing, you're always going to count the carbon to ensure we have the lowest possible number for your locant, which is the location of your substituent group. So if you count the carbon from here and the counterclockwise, that is going to be 1 and 5, or so forth. But if you try to count the carbon from here to the clockwise, it's 1 and 3. So obviously, we're gonna count the carbon from maybe 1, 2, 3 is right, or you can do counterclockwise also 1, 2, 3 here. So we now chose 1 and 3 over 1 and 5 because of the lower number combination. But also, the problem was maybe you can do this in a counterclockwise or clockwise to get the 1 and 3 and 1 and 3 anyway. So the last time what we talked was still we're going to follow the alphabetical order. Okay, so this one will come first. Then we want to give a 1 to ethyl group and 3 to methyl group. So we can have a 1 ethyl, 3 methyl, or how you can pronounce X. Okay. So this is the what we learned before. It's brief, just a review on the Friday lecture. I mean, last part of the Friday lecture. So the one thing I didn't cover beside this one was maybe what if we have not just a regular alkyl group, but some halogen groups like bromine or chlorine, like this one. Okay. So whenever you have this type of compounds, all you need to do is just treat this one as a alkyl group, like consider it as this one alkyl group. And to do that, what you can do is we normally just try to put the core name of that chemical elements and put the locant nomenclature. So this is bromine, so we're gonna just put bromo. Okay, so this bromine, its core name is brom here. So we're gonna put bromo. If you have a chlorine, you can say chloro. So this is the core name of that and all. So we're gonna put a bromo or chloro, depending on what element you have on that the carbon. So still, we're gonna do the same thing. The B or C comes first, and alphabetically order than M. So only thing you have to do is we're still going to count the carbon from here, okay? Because this is the alphabetically a bit more prior to M. So it would be maybe you can say, if that is the case, we're gonna say 1 bromo and 3 methyl cyclohexane. Okay, so this is the one we didn't cover in the last lecture. So probably I can give you some more example, maybe from here. Maybe you can try to do. Okay. Okay. In this case, how are you gonna name this one? Okay. So we're gonna keep the cyclohexane, right? For sure. Okay. And then probably we want to count the carbon from where is this one? Because this is maybe 1, 2, 3, and 4, 5, and 6. Okay. Because this is the bromine, bromo, what comes in first in alphabetical order, and also if you count the carbons, clockwise, you can actually get the 1, 3, and 4, which is the lowest possible number combination for locants. Okay, does it make sense? We good? So this will be what? 1 bromo, 3 chloro, 4 methyl cyclohexane. Makes sense, right? Good. Okay. So that's pretty much it. Yeah, go ahead.
So I know why we prioritize the bromo for the but why wouldn't we do 1, 2, 4 instead of 1, 3, 4?
1, 2, 4.
Because if we start with the methyl group as 1 and go up 1, 2, 4, wouldn't that be
so
less? Or are we prioritizing because
that's a
it's
good
3, 1?
question. I think that is that's sorry, that's good. That's a good question. I almost thank you for. So you can still count the lowest possible number here, right? 1 and 2, 3 and 4, and this is actually better. That's a good one. You got me. That's good. But you still need to order your substituent groups in what? Alphabetical. That's the key. But like I just did with the mistake, you always need to look for the lowest possible number combination. That's the key. So instead of 1, 3, and 4, 1, 2, 4 is lower combinations. So in this case, you need to count the carbon from counterclockwise. From here, maybe it's better. 2, 1, 2, 3, and 4, 5, and 6. That's very good. So in this case, still, but we need to put which one first? The alphabetical order would be what?
4 bromo.
4 perfect, yes. So it'd be 4 bromo, and there'd be this one. So it'd be 2 chloro, and 4 methyl. I'm sorry, 1 methyl group, and cyclohexane. 8, perfect. Makes sense, right? So first thing, the most important thing might be the finding a lowest possible number combination for your locant. So you know which way you can count the carbons from, and then you can try to order them by alphabetical order, which is B and C and M. So you can order them and your prefix with the locant, and you finish the nomenclature. Okay, sounds good? Perfect. I think I was confused with this one, but I drew it wrong. So anyway, so I think we can move on. Do you have any other questions about nomenclature? We get up. That's good. All right, so next one, we're gonna do some strain again. So I hope you guys remember torsional strain and the strain, right? So in that case, we talk about the ring structure, aromatic ring structure. We're going to talk about some the ring structure in carbons, the ring structure over here. Here's something I need to remind you of from the Jenkin 1 and 2 course. That is the carbon is group 4, right? So whenever it has bondings, if they're all single bond, right, there will be 4 bondings because there will be 4 available valence electron around carbon. It's group 4 elements. Okay, so if you think about this one, it's kind of easy to see this one as tetraplanar because if you look at this one like this, you might think this is only like 90 degrees apart from each bondings here, but this is in tetrahedral structure, means they're all going to be spaced, locate their bondings in the 3D, not on the 2D like this plane of the backboard. So what they do is they try to put the other 2 bondings like in this way, and the other 2 goes in this way, and bit spread than 90 degrees. So they can locate those bondings in 3D more efficiently. Does it make sense? Okay. So that case, you're going to have 109.5 degree from these 2 bond angles on carbon. Okay, that's the first thing you need to remember for this one. Okay, you guys remember this from Jenkin 2? With Jenkin 1, 2, or anything? Jenkin 2. So if that is the case, we have some problem here. What's that? If you try to look at the internal angle in this cyclopropane, it will be about 60, right? It was 60 degrees. Okay, so that means, okay, let me do this in more detail. Okay. In this way, they're going to have those 2 bondings are forced to 60 instead of 109. So it could have been spreader in a natural status, but it has to be even smaller angle. So that means for this one, it's a lot of pressure because they need to place in the very limited space. So if you spread it out, it's much easier, but they need to kind of squeeze in, right? Does it make sense? Good. And those all carbons are on the same plane too. So that makes those 2 hydrogens on the same side on each carbon. That makes total eclipse conformation on this side and this side as well. Okay. So if that is the case, this cyclopropane will experience a lot of discomfort. So to overcome that, this cloudiness, electron cloudiness here, you need to have some energy to keep their form. So normally cyclopropane is very unstable. Does it make sense? Because they don't want to be in this form, but if they need to, they're forced to. So they need to quite a lot of energy to sustain their cyclopropane form. Make sense? Okay. So here's the thing. If that is the case, maybe so here's the thing. Cyclobutane is it's just a square, right? So that here is a bit larger, but it's 90 degrees. Okay, and maybe cyclopentane is about. Can you guess the degree? It's 108. Okay, 108. And the hexagonal shape, the inner angle is about 120. Okay, so obviously this one will cyclobutane also experience quite a struggle for keeping this very small the angle degree here in each corner of this ring. Maybe this one is very okay. It's very close to 109. It's 108. Okay, cyclopropane is better. Maybe this is also the problem. It's too wider than it's supposed to be. So there's what the scientists back in the days tried to predict from using this angle from the wing structure. So this one also does have a somewhat struggle, but better than this one, for sure, right? And we're expecting this one quite okay, but this one also somewhat experience some discomfort here. But obviously, this is 120, but there is no problem there. So there's one assumption that is wrong here is what? You do this in this 90 degree, 60 degree, this is in plane for sure, but 90 degree, 108, or 120, when you assume it, they're on the plane, right? So in this if they're on the same plane as this black hole here, that is for sure 180 degree. But whenever they did the experiments, they're not on the same plane. So this cyclobutane is a bit slightly like a twisted, and this one is also too, and that one was almost perfect here. So this one too also experienced some discomfort to maintain the structure, but this one was fine because the carbons on the ring structure were not on the same plane. So they can always try to move up and down or kind of motion, because as I mentioned in chapter 3, which is a unique property of the alkanes, even just regular alkane or aromatic cycloalkane, they're all made in what? Carbons are made in single positions. This is perfect. So they always try to rotate. So that means though the carbons are not on the same plane, they can always try to change a certain degree of the angle somewhat in certain conditions. So those two were somewhat unstable, but this was fine. But if there's any discomfort that this company to experience because of the angle problem, we call this angle, literally angle strength or ring strength. It's up to you. But literally because of the angle problem. But now I just want to talk about why the cyclohexane was okay with this type of angle strength here. Okay? Does it make sense so far? We good? Okay, thank you. All right, so what you can do is if you try to look at so they're actually going to be not on the same plane, but they will make some kind of a chair conformation. Okay? Chair conformation. So we're gonna call this chair conformation because of this. So this is what, when you look this from the top to bottom view, okay, top to bottom like here. But if you try to put it in more in the side view, what it actually looks like is this one. You can try to draw the two tilted line in a space and try to do the predict on the like a linear wave. You can think as a linear wave and put the dot there over here. Okay? And what you can do here is you can try to do this line to like mirror image, almost like in a dot line. You can assume where that will be. And then all you need to do is connect those dots from two ends of lines like this. That's it. Okay? So I'm gonna show you why I'm gonna do this for chair conformation of cyclohexane. So first of all, what you need to do first is you see this shape here, and you see the points kind of pointing up, right? This point is pointing up, right? This point. So then put the line heading up there. Okay? And then same thing for here. So it goes up, right? It goes up. So we're gonna put one up, the line going up. And if you look at this one here, it's going down because it's heading down. It's heading down, right? This line is heading up right here. Okay? This is heading down. Okay? Heading down. So down, up, down, up, down, up. Okay? So here's the thing. If they can do this one, they are in here in this way. So you got the paper, right? If you have a paper looks like this one, try to fold this way. Could you guys fold the paper in this way? Like this. Yeah. Go ahead, fold the paper on this line, just fold it to the paper. And then whenever you do this, just one thing you need to do, just fold the other side and opposite direction. So you're actually going this way, okay? This way. So this is what this is. So this looks like a chair because it's like a chair you can sit on, right? So this is what we call this chair conformation. But as I mentioned here, you looking at it from top to bottom is still what? This shape right here. It doesn't mean it's transformed into the G form. No. You're still looking at the same structure, but it looks like this because it shows in different view, top side view. So now you for sure that is not on the same plane, right? If you look at this one on here, they're not on the same plane, right? They're on this same because they want to keep their original comfortable bone angle, which is what? Tetrahedral structure. Does it make sense? This is why cyclohexane does not have much of the angular strain, but also there's no angle strain, but also if you look at this one, it's quite interesting. One, down, up. And if you look at from the side in this way, this way, this way, this way, all the way up and down on each carbon, each carbon, each carbon, what kind of something you can, what does it remind you of in the chapter 3, later part of chapter 3? It's a staggered conformation. So that means there will be almost no torsional strain either. Okay? So that means this cyclohexane will be very stable. This is why this one is very stable. So let me keep going first. So whenever you do this, up and down, we call this axial group. It's like an axis, like a y-axis, vertical axis, go up or either down. Okay? But you're going to also draw you see there's the parallel lines. You try to go to this one to make it the tetrahedral structure. So you can same thing here, here, here. Okay? Explain to this one, right? And try to go this, here. Okay? So you see the lines doesn't go or either up and down, but goes parallel to the lines on here, 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 right? Here. That is what we call, they're not in vertical way. So we call this equatorial groups. Okay? It doesn't go either up or down, but on the sideways, which is not perfectly sideways, but parallel to the lines where they can find most likely, so that each carbon they can sustain the tetrahedral structure. I know it's kind of hard to understand at the beginning, but if you keep doing this, I promise you'll get it. Especially whenever you do this, you can actually look at from the top side view. So it's what it looks like here. Okay. But anyway, let me show you other type. Like I said, these two can always move right up and down. So if you do wing flip, this is what wing flip, you can do another structure. Looks like this. So I'm gonna do the same thing, but in the other way. I'm gonna fold this in the other way. So I'm gonna practice here. That connect the dot here, okay? And just like a mirror image dot line here, okay? And try to connect this dot here. Same thing. You can start with the axle first. So pointing up, 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 down, down, up, down. Point up, down, right? You see the down, okay? So then all you need to do is try to put parallel, okay? And try to do this, and try to get the equatorial positions. That's all you need to do, okay? So, yeah, okay? So this is what we call, actually looking at from this view is kind of confusing me anyway, but it doesn't make sense. Okay, wing flip. So wing flip doesn't mean it's you actually flipping the whole compound, no. It's just the different chair. So here, if you look at this one, you can actually see. You're looking at this one right now in this view, right? But in here, you're flipping in the other way. So now this is up and the other part is down like this, right? So they can always go up and down like this because it's a single bond. And this is all fine with this tetrahedral structure same. So either they can do it this way or this way, no problem. We call this ring flip. This is what it looks like with the equatorial axis groups on their cyclohexane. But once again, this is not the Z shape, this one. Does it make sense? Yeah, go ahead.
So just to clarify, the kind of original points for you, that would be your carbons.
Yes.
The other axial and those would be your hydrogens. In this example.
Perfect. That was my next part. That's good. So that was very good questions. So whenever you see this on exam, that's a very common exam problem. I'll show you right now. Here. So like you mentioned, if you already know in skeleton structure, we don't normally put the hydrogen on the structure. So you can technically, when you do this cyclohexane and this form, tail conformation, you don't have to show the groups. That's fine. But like we have some important, like functional groups, right? Like a methyl group, like we mentioned, chloro, bromo. Then maybe I can put this on here. Okay? So maybe you can still see, there's a hidden hydrogen here. But you just don't see it. But there is there, because this is a tetrahedral structure. But we know it's the exit point up, but it's with the bromine. So we can put that, but hydrogen, you can hide it. That's fine. Does it make sense? Okay? And then maybe in your exam, this is exam problem I cannot miss. This is so important because if you don't get this one, you're missing a major portion of chapter 4. So if you have this chair conformation here, now thinking about changing this one to here, because they can always go up and down. Then now this point carbon here, whatever carbon number 1 or 2, whatever you number, here, now here. Because it's gonna go and down. Like a paper, now it's going up here, now it's going down. So, and carbon is right here, right? Then, how are you gonna draw the bromine here? So you have 2 options, 1 and 2, okay? So what you can do, think about it. If you have a hidden hydrogen here, but this point here going down, heading in the equatorial position, heading up, but this whole part going down, then this hydrogen on the equatorial position will go to down exit point right here. Okay, and this bromine group will be now, heading down. Once it's heading up, now it's heading equatorial position. When it's wing flipped. This is something I cannot miss on the exam. It's very important. So make sure you guys do this. But if you try to do this as a paper I gave you today or any 3D model, they'll be a lot easier to look at. But I chose the paper because it can easier to do the flipping. That's why. Okay. There's a couple more things I want to mention. I wish I could remember everything that I wanted to cover today. But here we have chair conformation here. But once again, this freedom all have a freedom to move anyway. Now it goes up and down, up and down. Sometimes they can overcome those, so they can form. Okay. Maybe you can say this one. This is what we call boat conformation. So it looks like a boat. Let's draw this one again. Okay. Carbon, 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 carbon. Oh, maybe not this, but like more like this. Okay. Okay. And then this is what it looks like. So you folding each end of your paper on the same way, same face. So it's like a boat, right? Boat, right? Here, boat, right? So in this way, obviously, can you guys guess which one will be most stable? Is this one or this one?
Chair.
Perfect. Right? Do you see that already, right? Because these two groups are more proximity there, right? And then there will be some groups or either hydrogen or any group on there will experience what strain? Static, perfect. Static strain, perfect. Static strain here. Okay? So this is why this is more unstable than chair conformation. Both. Conformation. And then also, if you look at the hydrogen on those carbons are tend to more those ones are tend to more on the eclipse conformation on this side because of the positioning in the same phase, not going this way. So obviously, both conformation is more unstable than this one, or you can say less stable than chair conformation here. So sometimes what they do is whenever you have this one, right? Okay, both conformation here. But if you can twist it a little bit, not too much, but twist like a little bit like here. Twist like this one a little bit. That means you can minimize the static strain over here. Because if you twist it, it's not direct line, right? It's more diagonal distance. That makes the distance bit longer, right? And also there's eclipse conformation also kind of somewhat less eclipsed because it's twisted, right? So I'm not gonna do much in detail about this one, but if you twist this one in a bit of weird way, and we twisted both conformation. This is slightly more stable than this one because of that. Okay, that means this is slightly less unstable than this one. Okay, because of they can slightly minimize the static strain. Also, a bit of an eclipse conformation on the carbon on the bottom. Okay, so there's only one more thing that you need to know for this cycle and hexane conformation, but I'm not going to talk about today. Okay, just I want you to know about chair conformations, board conformation, because can always go up and down or up and at the same time. Well, you can also try to at some special condition. They may do this one because of they try to minimize the strain, they minimize discomfort they experience in that circumstance. This is why they want to do this in a certain condition and some by chance. So whenever you do this in the experiment, you actually see not always but by chance, and in a certain special condition, you have a more preferred confirmation over something because of the energy available in that space, the room, and the lab setting, and so forth. That is the driving force for the compounds to maintain a certain form, conformation form of same compound. Is it too much? Is it good? Oh, perfect. You guys are doing really great so far. Okay, so I think, let me see. Is there anything I'm missing like I did before? I think that's pretty much it for. So I'm gonna, what I'm gonna do, I don't think I'm missing anything today. So, so on Wednesday, I'm going to finish up I try to finish up the chapter 4 and possibly move on to chapter 5. And then Friday and Monday, we can hopefully try to finish up the chapter 5. And next Wednesday and next Friday, I'll spend the review session anyway. So you have plenty of time to just, review all the problems, potential problems you may see on the exam next Monday. Okay. So whenever you have any other questions, stop by my office. That's totally fine. But we'll still have a lot of time. Oh, and also I'll try to make some new assignment from Cengage. I'm working on it. I already got the accounts. I got your names, everything, and I'll try to put the enough time for the assignment, so deadline will not be somewhere near near the exam, but you can still do it before the exam, so you can do some practice on your exam. I mean, it's up to you, but I'll not try to push you into any deadline because we know we have an exam approaching in 2 weeks already. There's a big change in class. Don't worry about it too much. But I'll still try to put the assignment as soon as I can. So if you can try before the exam, that's good. But you don't have to. But I'll try to give you enough time for you, so you can do the Cengage assignment as either practice or for your later assignment after the exam. It's up to you guys. Sounds good, right? Perfect. All right, thank you guys. See you guys on next Monday. But please watch the video on YouTube on Wednesday and Friday.